So we'll start in 5 minutes. Waiting for others to join. So we'll start the session. So hi everyone. I welcome you to this live interactive session that is based on week 4 lecture module. So first I will be going to just briefly go through the lecture module and some of the lecture summary that has taken by sir. Then I will be going to discuss some of the problems related to that. That will be going to help us solving the questions present in the assignment. So, so week 4 module is started with the Hammaker constant, and so Hammaker constant for like particles. Let's say if we have two particles in a vacuum, then these are the two particles, and Hammaker constant is this. So, if we put these same particles in some medium, then what we have seen is that there is a decrease in the Hammaker constant due to the presence of some interaction with the solvent molecules. So that is the molecules are same, but now there is some interaction due to this media. And so we have this kind of interaction A1 to 1, which decrease the decreases the interaction. So the important point to note here is that medium influences the Hammaker constant. So if we have to define how it changes when we are having a two different, and we have to find the relation between the two like particles in the absence of media. So, so when we have particle, let's say this particle is I, this particle is J, K, and this medium is J. So J is the solvent, I and K's are the colloidal particle. And we have to find out the interaction. So in the lecture, it is already defined. So if it is 1, 2, 1, then it is derived as A11 half minus A22 to the power half. And it is derived. So I can quickly rederive it. And if it is A312, then it is A33 half minus A11 to the power half multiplied by A22 to the power half minus A11 to the power half. So A11 is the media or the solvent. So keep it in mind that A and 2 are the colloidal particles, two different kind of colloidal particles that is present in the media that is of type 1. So pseudochemical reaction as discussed in the lecture, pseudochemical reaction engineering approach is used where coagulation is coagulation leads to the formation of doublet. So as discussed like this, so we have let's say colloidal particle of type 1, let's say this is 1, sorry this is 2, let's say 2, and interacting with the media of type 1. Similarly, we have another set of it that has 2, and then we have 1, and so there is a correlation due to which there is a doublet formation. So due to the van der Waals attraction, two like particles come together. So the change in the interaction energy can be accounted as, so it is 1, 1, and this is 2, 2. So the phi becomes, so phi becomes phi 2, 2 plus phi 1, 1 minus twice of phi 2, 1. And in terms of chemical potential, we can call it as A 2, 1, 2. So 2 is the type of colloidal particle that is interacting in the media of type 1. So that comes out to be A22 plus A11 minus twice of A2. So this is the type of. So A21 we can rewrite by the mixing rule, that is A22 to A11 to the power half. So we have A212 is equals to A22 plus A11 minus twice of A22 A11 to the power half, and so it becomes A11 to the power half minus A22 to the power half to the power square. So any doubt till now? Any doubt? So let's do one question on this. So we have, what you have to do is you have to calculate the question is the interaction potential of water interacting with itself in vacuum is 4 into 10 to the minus 20 joule, while for typical hydrocarbon it is around 9 into 10 to the power minus 20 joule. Estimate the chemical constant for oil, water interacting across each other in vacuum. And options are 12 into 10 to the minus 20 joule, 1 into 10 to the minus 20 joule, and 2 into 10 to the minus 20 joule. So try this question and let me know the answer. I will be waiting for your answers. Okay. Haruni and Dipanvita. Hello, am I audible? Can you please unmute yourself and let me know if you are trying this question? Tarun?
Yes.
Dipanvita?
Yes, sir, I'm doing it.
Okay, okay. Just try it and let me know the answer.
Okay, okay, sir.
And we'll see the solution. So Devaru?
Option C, sir.
Option C. According to Tarun. This is given by Tarun. Let's see what others say. Do it carefully. It's not that tricky, but read it carefully. Devaru?
Yes, sir.
So we have just discussed about the Hamaker constant, and this is one of the question that I've given. So just try this.
Sir, can you please revert back to the like first page that you like taught?
No, just this one. That's about Hamaker constant and how it changed when there is
So
some.
my answer is
Okay.
C.
What is that?
C, C.
Dipanvita is also saying C. Okay. Okay, let's wait for Debarun and we'll solve this question.
Sir, hello.
Yeah,
Yeah, it is C only.
see,
Yeah,
let's see. So the interaction potential of
because
water
it
in,
is half 3 and 4 is 2, so 3 minus 2, 1. And 10,
let's
10
see,
on that up.
let's see. So the potential of water interacting with itself in vacuum is, so let's say water to be of first kind and hydrocarbon. Is second. So A one is given as that is 4 into 10 minus 20 joule, and A two is given as 9 into 10 minus 20 joule. Now we need to estimate the Hamilton constant of A oil water in vacuum. So that is A12. We just need A12. There is no medium in between the two. We just need 1 and 2, and that is in vacuum. So the medium is vacuum, so that's why it's A12. So A12 means A11 into A22 to the power half, and so it becomes 4 into 9 to the power half into 10 to the minus 20. So what it becomes is 6 into 10 to the minus 20 joule. The correct option is this. Any doubt? Did you get the point? None of you read the question carefully.
So there is vacuum inside it. Okay. I didn't
Yeah,
know
it is
that.
written. Yeah, it is written. Any doubt? Others? They
Sir,
were, yeah.
oh, I got it wrong. Sorry, sir. My
No, no.
bad.
Yeah, yeah. Okay.
Sir, can you explain this again?
So this is all right. A11, A22 is given. That is also fine. Now we are saying oil and water is interacting. So there is a interaction between the molecule of water to that of molecule of oil. So A12, and that is in vacuum. So when there is no medium, then it is vacuum, and we say that it is sort of like this when there is no media present. So vacuum is equivalent to no media. So there is no media. If I say that no, it's not vacuum, it is some other media. Or I can say that oil and oil is interacting with each other in a water. Then it's sort of 1 to A, 1 to 1, something like that will be there.
Okay.
Now did you
Okay,
get
sir.
Sir, if there is
Yes,
any
sir.
medium, then A212 formula is applicable.
what?
If there is any medium instead of vacuum, then A212 formula is applicable.
Yeah, then only that medium depends. Now, if I say that, let's say I want to find the interaction of hydrocarbon molecule with hydrocarbon in the presence of water, then I have to find A212. If I say the interaction of water with water in the presence of hydrocarbon, then I have to find A121. And if I say A water, then A11 in the vacuum. If hydrocarbon, A22 in vacuum. Hydrocarbon and water, then A12 or A21 in vacuum. Did you get that?
Okay, sir.
Okay. So now next question, and so let's look at what happen if we are having a two different kind of. So apart from this question, there is some generalities that are discussed about this A212 is, so some generalization discussed are. So first is that A212 is always positive regardless of the relative magnitude of A11 and A22. Why? Because A212 we get the formula that is A11 to the power half minus A22 to the power half, and it is square. So when a square is there, then it is always positive. And so we can say that identical part exerts a net attractive force on one another in the presence of medium as well. So this is the important point to note, that the net attractive force is there in the presence of medium as well. So we know that when A is positive, then it is all to be attractive. And if it is negative, then it's repulsive. The second generalization is that if A11 is equals to A22, then it means that A212 is always 0. So which means that we can tune the solvent medium interaction. Or solvent medium conditions. Now let's look at, there is a correlation between two different kind of molecules, two different kind of colloidal particles. So we have let's say one of this kind, but the dispersion media is said the solvent is same. The solvent is same. Which means leads to so this is let's say 2, this is 3, this is 3, and there's the doublet. This is due to coagulation, and there is a that is the net change in energy comes out to be that is I am calling as Phe because later I guess we will be going to use Phe as a concentration of the polymer in a dispersion media. So let's call it as Phe. So Phe 23 plus Phe 11 minus Phe 21 minus Phe 31, and so it becomes Phe 23. So we have to find now A213. So these are the two kinds of colloidal particle, and this is the media. And this is media. So A23 plus A11 minus A21 minus A31. So we can replace so A11 as it is, A23 becomes A22, A33 minus A22, A11, okay, take half inside, minus A33, A11. Let's collect A11. I can put like this also. Then A22, if I collect, it becomes A33 minus A11 minus A33, A11 to the power half. If I take this one and this term, 11 to the power half, and I take A11 to the power half minus A33 to the power half plus A22 to the power half, 11 to the power half. What we get is A33 minus A11 to the power half plus A, sorry, multiply by A22 minus A11 to the power half. Is there any sign mistake? So this become common. So this become negative. So what I do is A11 minus A33 to the power half, and this becomes A. Can you check if there is any sign mistake I did? So let's look at this A11, A22, A3 to the power half, A22, A11, and A11 and A33. Okay, that's fine. So A22 is taken common, A33 half minus A11 half is there, minus A33 half, A11 half. Now I took A11 half common, A11 half minus A33 half plus A22 half, A33 half minus A11 half. Now I took A33 half minus A11 half common, multiplied by A22 minus A11 half. This should be, yeah, this is correct. So 1 minus will come out. So this is correct. Okay.
Sir, A22 half, sir.
What? Oh, yeah. Thanks. So, so I have a question for you on it. The question is this. To calculate the chemical constant for the online system. So first is you have used parts that is of one type. Then media is here, and it is interacting with tetradecyl. You have to find A1, 2, 3. Second is fuse quad. Fused quartz and octane. So you have to find, you have to find 1, 3, 2. So fuse quartz is interactive with air in tetradecyl. Fuse quartz is interactive with fuse quartz in octane. Here also 1, 3, 2. It's essentially becomes 1, 3, 1. Then we have mica interacting with mica in water. It becomes A121. So given that for the case of so let's don't take it. Let's take so A11 is given as 6.5 into 10 to the minus 20. A22 is 0. A33 is 5.1 into 10 to the minus 20. So that is for the case of first. For the second case, we have so A11 is same, that is 6.5 into 10 to the minus 20, and A3 is 4.5 into 10 to the minus 20 G. So for the first case, options are minus 0.33 into 10 to the minus 20 Joule, minus 0.66 into 10 to the minus 20 Joule. Then I have 0.33 into 10 to the minus 20 Joule, and 0.66 into 10 to the minus 20 Joule. For the second, the options are minus 0.18 into 10 to the minus 20 Joule, minus 0.36 into 10 to the minus 20 Joule, minus 0.36 into 10 to the minus 20 Joule, and then minus, so this is plus, this is plus, minus 20 Joule. Okay, so try this question and let me know the answer, and then we'll solve it. Okay, we'll be waiting for your answer. So any answers?
So option D.
For the first one.
Yes, sir.
For which one?
Sir, first one. C or D? My calculation. 1 second and check.
Any other? Arun?
For first one, option B, sir.
Option B. Okay. And what about second?
Doing, sir.
Okay. Devan?
Yes, sir.
Did you get the answer?
No, I'm doing second one.
What about the first one?
Sir, can you repeat?
What about the first one?
I'm option D.
Option D. Okay. We'll see. So can we solve first one together and then see? Okay.
Yes,
so
sir,
let's
you can.
try first one. So here quartz is interacting with air in the medium, that is tetradecane. So we have to find A1,
1, 3, 2.
3, 2. We have to find A1, 3, 2. And the formula that is there, it is so medium is
Excuse me, sir. For
Yeah.
second one, option D, sir.
Sir,
Option-
first one, option B.
first one, option B. Okay. Second one,
Option D, sir.
D. Okay, we'll check. We'll see. So who solved Dipanvita, can you tell how you have solved the first one?
Sir, A22 to the power half minus A33 to the power half into A11 to the power half minus A33 to the power half.
Into A,
11 to the power half
yeah,
minus A33 to the power half.
okay. And why like this? What do you think about
Sir, the formula that you have given, I have arranged it in that way only.
Okay, so here the media is 3. And these are the different kind of so two other so these so the media is this. So these we are looking at the interaction between 2 and 1 in a media that is 3. Okay. So this is correct. And so let's put the values here. So A22 is 0, so it becomes minus of 5.1 into 10 to the minus 20 to the power half. And A11 is 6.5 into 10 to the minus 20 to the power half minus 5.1 into 10 to the minus 20 to the power half. Okay, so can you tell what are the values you got? So 10 to the minus 20
Minus, sorry, 0.29.
from root of 5 point what?
Yes. 0.29 into 10 to the power minus 10.
0.29 into 10 to the minus 10. From where you got this?
Yes, sir.
It's the root of 5.1.
Yes, sir, probably. And the other one I've got minus of 2.25 into 10 to the power minus 10. No, sir, this will not be minus. Minus 2.9, no. First one,
So so let me calculate it. So for making it easy, let's take out 10 to the minus 20 common. So it becomes
yes,
10
sir,
to the
yes.
minus 10, 10 to the
It
minus
will be-
10. So it
Sir,
becomes
I found out.
10 to the minus 20. Yeah. So what is the root of 5.1?
2.25.
Yeah, 2.258 with minus sign.
And the other one will be 0.29.
Yeah, let me check it once. 6.5 minus 1. What you're getting? Other one is?
0.29
Yeah, correct.
into 10 to the power 10. Oh, yes, I have written that.
So it becomes
It becomes minus 6525.
so minus 0.658 into 10 to the minus 20. And the closest answer is this. So this was correct.
Yes, sir.
Okay. Now what about second one? The second one is we have to find the interaction of two like materials in the presence of media that is octane. So we have to find 131. So who solved this? Who told me this? Dipanvita?
Me, sir.
No,
Dharmi,
sir,
sir.
I have not
So
done.
can you help me solving this question? The second one.
Yes, sir. A11 power 1 by 2.
A,
11 power 1 by 2
yeah,
minus A33 power 1 by 2
okay.
into A11 power 1 by 2 minus A33 power 1 by 2. So it is the whole square, sir. 6.5
Yeah, so
into
it
10 power minus 20.
you can, yeah, it's like this only, like one-to-one interaction. Yeah, this one.
Yes, sir.
So it should be positive. So for
Yes,
sure,
sir. Yes,
these
sir.
two answer cannot be possible. And so A11 is
6.5
6.5
into 10 power minus 20 whole power of 1 by 2.
minus
4.5, sir.
4.5.
Whole power of 1 by 2.
So that will become 10 to the minus 10 and square this, so it becomes 10 to the minus 20.
Hmm.
Okay, so 6.5 to the power half. So what did you get this? So 6.5 minus 4 point minus in the root of 4.5. So it becomes
0.425 whole square, sir. So it becomes 0.18 into 10 power minus 20.
and so what we get is 0.18.
Into 10 power minus 20.
Okay, so this is the correct option. So any doubt in this till now? So what we have discussed about the Hamaker constant.
Sir, doubt, sir.
What?
When the medium is kept between two particles, how does it affect the Hamaker constant, sir?
Are you asking me the answer or are you asking me the reasoning, like why it is So
I'm asking with the reason oriented, sir.
okay, so when we are so what happens is like that when we are having a two interactions, like two particle interacting with each other in a vacuum, so there is no so the interaction between two is not affected by the third media. So whatever the interaction is the pure interaction between the two media. But when there is a third media present, so due to the third media, it depletes the interaction between the two. So due to that depletion, what happens is the interaction between the two in the presence of media decreases. And that's why this interaction, if you see that we have discussed it and sir has already discussed in the lecture, so that is there is a decrease in the Hamaker constant in the presence of media.
Yes, sir.
Is it clear?
Yes, sir.
Okay. Anything else about Hamaker constant? So once we are done with Hamaker constant, we will be moving towards the colloid polymer mixture and we'll look at the depletion and the static effects as discussed in the lectures. So any doubt about Hamaker constant, any kind of doubt? And using this Hamaker constant, as you know that we are able to calculate the interfacial tensions. So any doubt?
No,
Parul,
sir.
Dipanvita,
No, sir.
Devaru, Shweta, hello, am I audible? Okay. So this is all about the Hamaker constant that we have discussed till now. So now let's look at the another section of the week 4 lecture that is mostly on the presence of polymer in the colloidal dispersion. So colloidal poly as discussed in the class, why we add colloids to the polymer is due to different kind of applications. We can do viscosity modification of the colloidal dispersion. Then there are many others like in ceramic processing, as binders. Then so these are some of the reasons like why we uh, we have to make the colloid polymer mixture, and so there is a discussion on like what is the effect of what is the effect of addition of polymer in colloidal dispersion. So the effect is there is flocculation, there is gelation, there can be crystallization, and there can be glass transition. So these are some of the effects that is happen when we add polymer to the colloidal dispersion. And what are the parameters that controls the phase behavior of colloid polymer mixtures that are, so the most important parameter is Q, that is defined in the lecture as the size of the polymer to that of the size of the colloidal particles. The size of the polymer uh, is this Rg, which is the radius of gyration, and the size of the colloidal particle is R. So if it is already discussed in the lecture that if Q is less than 0.5, then we are in the colloidal limit. And if Q is greater than 2, then we are in the protein limit. So all are these details are already discussed in the lecture. And we have already also seen that what is the good and good and bad solvent. So good solvent are those which favors solvent protein interaction, sorry, solvent polymer interaction. Due to this, there is an expansion of polymer coils. And bad solvent are those where polymer self interaction is favorable compared to the polymer solvent interaction. So these are the definitions of the good and bad solvent that is discussed, and then there is a discussion on phase diagram that how the volume fraction of the polymer will affect the phase change from fluid to gas and then to gel. So now directly look at the now we will quickly look at that there is the some other terminology that are discussed that are bridging flocculation. So bridging flocculation happens when in the case of low polymer concentration, when the polymer is adsorbing. absorbing tide, then bridging population happen. And what happen is that, like, you have two colloidal particles and there is a adsorption of polymer, the ends of the polymer chains, and due to this there is a bridging, something like this. So that is the bridging population. Then, so this happens at low polymer concentration. Then we learned about steric stabilization. In case of steric stabilization, at moderate to high polymer concentration.
सर्विसिंग
Shweta, can you unmute? Can you mute yourself? So at moderate to high polymer concentration, there is a polymer adsorption over the colloidal particle, and you have some brush-like structure. So we have like this, some polymers at chains adsorbed, and due to this they're having a brush-like structure form. So this is called to be a steric stabilization. Then the most important thing that we will be going to discuss is, so any doubt till now? Anyone has whatever in any of this concept?
No, sir.
Okay. So then we have depletion population. So depletion population, what happens in depletion population is that when you are having a colloidal particle, that is very close to each other, and there are polymers present. Polymer presence in the media. So what happens is that around the particles, there is a polymer that are present, but in this region, if you see in this region, so this diagram is for the case when polymer are are of or I can say non-absorbing polymer. That is for the case of non-absorbing polymer. So what happens is that, so in this, if you say this lines-like structure. So that is already discussed in lecture. So what happened is that there is no polymer able to go inside this, and this happened when the distance between this is, let's say, h. H is less than of twice of Rg. So that is the size of the polymer. So due to this, what happened there is, so this is a depletion zone. That is formed, and due to this depletion zone, what happens is this cause a osmotic pressure, due to which particles becomes colloidal particles becomes closer to each other. So what happens is that, so because there is no pressure, and these outside the polymer molecules pushing this, as the pressure is zero here, so if let's say this is Pi and this is P naught, so Pi minus P naught is greater than zero, and due to this, what happen is, so P naught is higher actually. So due to this, there is, so these polymers molecules are pushing this towards each other, and there is some sort of an osmotic pressure present, and the force of interaction we called it is this, that is NKBT, which are pushing this to pushing the particles towards each other. So it is already discussed in the lecture that depletion population can be of can be caused due to different cases. So first case is this: when you are having particles, colloidal particles with non-absorbing polymer. With non-absorbing polymers, then there is a possibility that this depletion region formed when we are having a adsorbing polymer. Then we have colloidal particles with nanoparticles. So when we have some big particle, and so this will create a depletion zone, or we are having particles with micelles. So all of this can leads to the depletion population. So any doubt in this? Any sort of doubt? Well, yeah, hello Shweta.
Yeah, actually, I have joined it quite bit late. Can I take the snapshot of the previous thing, what you have discussed?
This one?
Not this one. From the beginning, actually. I joined it quite late, so.
Yeah, most of the part is already in the lectures. Only the questions are different. So
You, the questions ones,
the video
actually, I
and
joined. Yes.
the video and the notes will be uploaded on the Swayam portal.
Actually, you upload these videos quite late, so it cannot help me in solving out the assignment. So for that, I want.
Okay, so on Friday, I guess I have uploaded all these videos.
Actually, we have to submit the assignment by Wednesday, so that's why problem.
Okay,
So
okay.
can I?
Yeah, but this time I will. I don't know about that, so but this time I will upload it on time.
Monday.
Yeah, today's Monday, so by tomorrow I will be going to get this recording, then we'll upload it.
Just a prior of it, can I take the snapshot, please? For 1 minute, it will be.
Yeah, you can take.
No, in the beginning. Before that, there is also you have shown us. Yeah.
This one.
So from the beginning.
So this is already discussed in the lecture, all about this, all of these.
Yes, below that.
Only this numericals we have discussed.
That's numerical solutions actually.
Anyone has any doubt apart from that?
No, sir. Sir, I was having a problem in the assignment problem, which was given h equals to 16, h equals to 8, and h equals to the separation distance it was given. I was having a problem in that type of problem. If you make us solve that type of problem, then it will be very okay.
Yeah, I will be going to solve one of the numerical on depletion population, but I hope that will help you in solving that numerical, but not directly to.
Can you scroll it? Can you scroll it? Wait. It's a blue one. So
this is already present in the lecture.
yes.
So this is
No,
already
this
there in the lecture.
worked out for the problems that you have taken for the water and hydrocarbon. That's what. Yes.
Yeah.
No, not the problems. I think below it. Just the solution. Yes. Wait. Yes.
So any doubt related to the fundamental understanding of the population depletion? So why it is happening, how it is happening? Okay, so
Yes. Thank you.
while in the depletion population, we have learned about the depletion interaction, and so in this case, what as discussed is that the depletion potential. So it becomes infinity when H is less than 0. So when the two colloidal particles are very close to each other, then this depletion potential goes to infinity. When it is greater than of twice of Rg, in the lecture it is 2 delta. So essentially both are same. So when it is So when the two colloidal particles are far away, such that there is a possibility that this depletion region will not be there, and polymers are able to come in between the two colloidal particles, then the interaction between this depletion interaction is also is zero. But in between that, when there is a formation of depletion zone and there is a pressure uh, that is formed, that is the osmotic pressure that is present. So this osmotic pressure that is formed due to the pressure difference between this region to that of the outer region, and so what we call, so the depletion interaction comes out to be PV, and this is in the region when H is greater than 0 and less than twice of Rg. Okay. So, if for the case of spherical particle, we,
Shreyank,
yes,
hey Shreyank,
yes,
hi. Hey, this is we minus PV.
yeah, yes. Yeah, this is minus P. So we for the case of a spherical particle is given as pi by 6 2 del minus h square 3r plus 2 del plus h by 2. So all this will be derived in the next module, that is week 5 module. So on this, let's do one numerical related to this. So this is for the case of spherical particle, but if let's say we are having a plate-like particle, that is also discussed in the lecture, some kind, and there is some, that is this distance h between this. So the interaction between, so interaction can be calculated as, this becomes PV. So that is same, only the V that we are calculating is just, so this is 0 if H is greater than 2 delta. If H is less than 2 delta, it becomes N B E. This becomes N KBT into 2 delta minus H. So that is for when the case for the colloids are of this plate-like, or the some colloidal rods are there. So we have this kind of interaction, and for this case also P is N KBT, and is the number of polymer molecules. Okay, so let's solve one question on it. The question is, consider a dilute dispersion of a colloidal rods that has having a length of 4 micrometer and width 2 micrometer a small amount of non absorbing polymer of radius of gyration that is 2 nanometer is added to the colloidal dispersion. The concentration of colloid polymer mixture is 10 to the power 20 molecules per meter cube.
Shreyank, I just want to add something, Shreyank, here.
Yes.
See, I mean, I think this dimension that you're taking, right? The length of 4 micrometer and width of 2 micrometers is fine. But I think instead of calling it as a colloidal rods, you could think about this more like maybe a rectangular particle because these formalism that you're discussing, right? It is typically valid for cases where you have flat surfaces.
Yes. Yes.
Okay, so therefore, I mean, you could have this considered dilute dispersion instead of colloidal rods. You could say maybe a plate-like particles or something like that. That's more appropriate.
Yes.
Yeah.
Yeah. Thank you. Plate-like particles. So it has the plate-like particle. So this is discussed in the lecture. It is valid for the, so when we are having a plate-like particle having some area. So the concentration of the colloid polymer mixture is 10 to the power 20 molecules per meter cube. Assume that dispersion is at 300 Kelvin. Calculate the depletion strength when surface to surface distance separation is 1 nanometer, and options are 0, minus 4.8, minus 1.2, and none of the above. So you have to calculate this and calculate it in terms of KBT. So whatever you get from the interaction, just divided by KBT.
The answer will be in the negative, right?
Yeah, that for sure. So you can take some time to solve it, then we'll discuss its solution.
Sir,
Hello? Yeah.
so here R and delta will be same if we apply the formula of pi by 6 into 2 delta minus h whole square into 3r plus 2 delta plus h by 2.
No,
Uh,
no, actually this is valid for the spherical particles. This is mentioned already as Perez also pointed out, this is a plate-like particle. So that's why it has some area. And we
so
have this
this formula
interaction
will be
energy
applicable.
per unit area that is given by this. So
Okay, sir.
yeah. Also keep that in mind that this interaction energy is per unit area. So you have to multiply it by the area of the particle.
Sir, do we have to keep all the units in nanometers only?
No, do it in SI units.
Okay, okay,
It has to be calculated in terms of kBT.
okay. So my answer is coming 2.4 minus 2.4.
2.4. So that is
Minus 2.4, yes.
We'll wait for others. Let's do it. We'll try. So let's try this question. So Dipanvita, you have answered this 2.4, right?
Yes, sir.
Yeah. So can you help me in solving this question?
WH equal to minus N kBT
Hmm.
into 2 delta minus H into A.
2 delta minus H into A. Okay.
Since H is less than 2 delta.
H is less than 2 delta because H is 1 nanometer and 2 delta is, or 2 Rg, that is 4 nanometer, correct?
Yes.
And N is given as and there are 20 molecules per meter cube. Okay, so we have to find it in terms of kBT, so we'll keep it aside. So minus n into 2 delta minus h into A into kBT. So we have to find just this factor. And
Yes.
so n is
10 to the power minus 20.
minus 10 to the minus 20 to
So 10 to the power 20 it will be.
what?
So n equal to 10 to the power 20 and not minus 20.
Yeah, yes, sir. And area is
2 into 10 to the power minus 6 into 4 into 10 to the power minus 6. Answer, we have to convert from the nanometers to meters. So 2 into 2 into 10 to the power minus 9. That will be.
so this is because of this.
Yes, yes.
What we get is
24 into 10 to the power minus 21. Into 10 to the power 20. No, sir, into 10 to the power 20. No, sir, I'm saying that into 10 to the power 21 into 10 to the power 20.
1 minute.
10 to the power minus 21. Yes, yes, yes. Into 10 to the power minus 21. KBT. Yes, sir. This is the answer.
Yeah, so this become minus 2.4. So the correct option is none of the above. And so this is this. Others are able to solve this or having doubt in this question. So this could be the last question of this session. And if you have any other doubt, we'll discuss. Taruni,
Yes, sir.
are you able to solve this?
Yes, sir.
Okay. Debanu,
Yes, sir. Now I have understood.
okay. Shweta,
Yes, I have understood. Yeah.
okay. So any other thing you want to discuss from the week 4 lecture? So we have discussed all of this about Hamaker constant. Some questions on Hamaker constant we did. Then we'll discuss about this polymer solutions, depletion interactions, and then numerical. Any doubt? If you don't have any doubt, then I will be here if you have any doubt, but if you don't have, you may leave.
So, will there be any problem solving sessions before the exam?
Yeah, so these problem solving sessions will help in exam also. So that is for every week. So it's on every week lecture. So I guess it will be going to help in the final exam also.
Yes, sir. No, I'm asking if there will be any separate problem solving session for the exam.
I don't think so. Something like that is not scheduled. If there is any, will inform you that.
Okay, sir.
Okay.
So, can I leave?
Yeah.
Okay, sir.
Can I just explain that Hamaker constant, actually, the question which is given in the assignment, it is a spherical particle. Once it was, when it was in a vacuum and then it was immersed in the water. So, okay.
Hello.
Yeah.
Hello. Yeah.
Yes.
So what? Can you
So,
complete the question?
so I have a doubt that in the assignment it has given an a Hamaker constant for a pair of spherical silica particles. when it was immersed in the, when it was present in the vacuum and when it is present in water.
Okay.
So, but the question is asked to determine the effective Hammaker constant, dictate the van der Waal attraction. So, I don't able to understand what I need to do over here.
So that's what I discussed in this in the start, is that like when you are having a water. So this question, if you see, we are calculating the interaction of, let's say, if what the interaction between the water molecules in vacuum is something like this, and hydrocarbon molecules with themselves in is something like this, and we need to find out the interaction between each other. So we have to calculate this kind of interaction. So this is the case of when this is this case. Now, if you look at this case, it is there itself in the lecture. Like so, if you see two kind of particles are there. That's a pair of particles in vacuum. So that is the interaction 1 1. But if it is some medium is present, that is some kind of media that is 2 that is present. So we need to find A1 to 1. And so the effective A1 to 1 we have derived as this A11 to the power half minus A2 to the power half to the square. And we have derived it from this approach of coagulation, that is the pseudochemical reaction approach. There is a, so this is the A1 to 1 is essentially that that you are talking of. That is the effective.
Actually, I want to ask, there is a same particle, that is silica particle. It was given it as a Hammaker constant for a vacuum, and that same particle is immersed in the water.
Yeah. So
When
that's
it
what.
is
So
present.
that's what we have discussed. So 1 1 is in vacuum. So the same kind of particles in vacuum. Now we have same particles in a media, that is some kind of media that is kind of 2 that is there. So now we have to find the interaction between 1 and 1, but in the presence of media.
Yeah.
So in the presence of media, the effective Hammaker potential is become this A1 to 1.
Yeah.
So that is this.
Okay. But the I didn't understood about that. What is the determination of that means that question is asking me the effective Hammaker constant, right?
Yeah, so that is the effective Hammaker constant.
Yeah.
Yeah,
Okay.
so
Can
what's
you
the
scroll? Oh, okay. Can you scroll a little bit lower to that? No,
Yeah.
up, not lower to, yes.
Yeah.
Yeah, I understood this part because in the video I understood, but the question what I exactly asking I was not able to, when it is written that van der Waal force of dictate the van der Waal force of attractions. So for that I am having the doubt.
So a Hammaker constant is essentially telling you about the van der Waal forces of interaction only.
That is for sure.
So
Problem, please.
what?
The next problem that you have worked out.
Yeah.
Yeah, 1 second, please. Let me read the questions. Yeah. Yeah, understood.
Okay.
Okay. Can you scroll a little bit lower if you have discussed it? Okay. Identical particles not in okay. Yeah. It's a little bit more lower. Next page, please. For quartz and air and tetraoctans. Okay, you'll find out that one. Can you show me these solutions? Yeah. So that means I understood that we have to substitute the values in the formulas and get the answers for the Hammaker constant, right?
Yeah, but if you are unable to understand the concept that how the medium and the particles you have to take, then you will be going to solve it wrong. So you have to keep that in mind.
Yeah. That means we have to keep that medium inside in between the both the number. The particle should be in the outside and the medium should be inside, right?
Yeah, mostly it's like that.
Yeah, that's what is given in the lecture videos.
Yeah.
So if you uploaded it, it's by today or tomorrow, then it will be definitely helpful for me actually.
Yeah, we'll upload it by tomorrow as soon as I get this recording.
Please do it.
Okay. Anything else?
No, nothing. Actually, I joined a little bit late, so that's why it's a problem. Thank you so much.
Thank you.
Thank you, sir. It's okay.
Thank
you. Okay, welcome.
You can leave the meeting. Yes.
Sure. I will leave the meeting.
Yeah.
Okay, sure.
Yeah. You can stay back. Maybe we can, you can switch off the recording and then we can talk a little bit.
Yes, sir. So actually, so this recording is automated. So that is.
Is that sir? Okay, no worries. Then maybe I'll give you a call. We can talk.
Yes, sir. We can talk. We can talk on
sure.
WhatsApp. Yes.
Okay. Yeah. Bye.
Yeah. Bye.